Automatic landing systems must reduce the rate of aircraft descent for safe touchdown. This is the final phase of landing, called the flare path. The flare path is the second of two phases in automatic landing control. In the first phase, known as the glide path, the aircraft controls its velocity about a transmitted glide slope from the runway. Closer to the runway, the aircraft transitions to the flare path, where the rate of descent is slowed for safe touchdown. In this lesson, we go into the details of an automatic flare path control system. Successful piloted flare paths follow an exponential path to touchdown. So, we define an exponential path we wish to follow, where h0 is the altitude at the start of the flare path, h is the instantaneous altitude, and tau is the desired time scale of the exponential descent. The geometry of the flare path is embedded in tau, so our first objective is to determine tau, that is, the time scale of the rate of descent from the geometry of the flare path. We first ask how many time constants tau should elapse before the aircraft touches down. Let n be that desired number of time constants. Let's now parameterize the time constant based on the flare path geometry. To travel from the start of the flare path to touchdown, we need the horizontal velocity. This is airspeed times cosine of the glide path. But the glide path angle is small, so horizontal velocity is approximately airspeed. Now, to touchdown, the aircraft first travels from h0 to the transmitter, then from the transmitter to touchdown. Thus, the total distance traveled, r1 plus r2, is airspeed times total desired time on the flare path, that is, n times tau. Solving for tau, we get it as a function of r1, r2, vt, and n. But r1 can be determined from the geometry of the glide path. Note this triangle. The tangent of the glide slope is h0 over r1. But again, glide slope is small, 3 degrees is typical. So the formula simplifies. And now, for the moment, let's focus on determining that initial altitude. Recall the desired altitude path. Take the derivative and we get an equation for the desired altitude rate. Substituting the altitude at the start of the flare path, we get an expression for the initial rate of descent, h0 dot, and then we solve for h0. But note that at h0, the velocity is tracking the glide slope, assuming the glide slope controller is working well. Thus, the initial rate of descent is simply airspeed times sine of minus glide slope angle. h0 dot is approximately airspeed times minus glide slope angle. So, substituting for h0 dot, we now have an expression for the initial altitude. Bring this back over. Substitute. And ultimately, we get that r1 is airspeed times the time constant tau. Bring in the formula for r1 into our expression for total range to touchdown, and now solve for tau. Ultimately, getting an expression for tau in terms of r2, airspeed, and the desired number of time constants to touchdown. As we showed before, the desired exponential flare path can be differentiated so that the rate of descent is -1 over the time constant times altitude. Given the aircraft present altitude, then, this expression provides the desired rate of descent, h dot command. The rate of descent command model is a key element of the flare path control architecture. In the longitudinal plane, flare path control involves two main loops, the airspeed controller up top and the rate of descent or h dot control on the bottom. We developed these controllers by first looking at the closed loop aircraft control. That is, the combined airspeed and pitch control acting on the rigid body dynamics. This results in a single closed loop process, which then we connect with altitude dynamics. This forms the plant for flare path control, a single process. The flare path control connects through the pitch angle command input. Altitude rate are fed back, and the flare path controller provides that command to pitch angle to maintain the flare path. Ultimately, we close the loop between the plant and the controller, resulting in a single closed loop system that describes flare path tracking control. We start with the dynamic controller for the longitudinal aircraft. First, focus on the airspeed control. The airspeed controller is proportional integral that acts on airspeed air. To compensate for the slow engine response, a lead compensator is employed. Breaking out the lead compensator, we can see the architecture for both systems, and we can represent the PI control and the lead compensator as LTI state space processes. We connect them in series to get a single LTI system for the lead compensated airspeed control. Now, the pitch controller has proportional control on pitch angle air with artificial damping. That is, proportional feedback on pitch rate. A lead compensator is also added here with similar structure to the airspeed lead compensator. It's used to improve pitch tracking response and ultimately represent this as a single LTI process, so that both pitch and airspeed lead compensated controllers can be combined into a single 2-input, 2-output controller. We have then the control in the frequency domain and, as an LTI system, them combined in the time domain, where R is the aircraft state command, Y is the plant output or controller input, and delta command is the control effect command going in to the aircraft control actuation systems. The end result is a combined process receiving commanded airspeed and pitch angle inputs, receiving achieved airspeed, achieved pitch angle, and achieved pitch rate, and outputting the desired throttle and elevator to the plant. This is mathematically captured with a single state space model. Now, to close the loop, we need a model of the aircraft dynamics and the control actuation systems. The controller acts on the rigid body dynamics with basic control actuation system models. Here, the rigid body contains the short period and the phugoid modes. The input to the rigid body modes are the achieved elevator and achieved thrust. First order elevator, throttle, and engine actuation system models are used. Let's look at the elevator input channel. The elevator itself is modeled as a servo process with a first order system. It receives a lead compensated elevator command. The thrust comes from the engine. It is also modeled as a first-order process. It receives a lead-compensated thrust command. Preceding that is a throttle model. It's also a first-order system. The control actuation systems can be grouped as a single process and then connected in series with the rigid body state space model. So we get a single LTI model comprised of the CAS, control actuation system, and the rigid body dynamics. It receives elevator and throttle commands from the controller and produces the aircraft state response with selected output, airspeed, pitch angle, and pitch rate. We now have the plant and the controller. We're ready to close the loop. We've just developed the plant model, and prior to that, we developed the airspeed and pitch control system. So we connect the plant output to the controller input, and the controller output to the plant input. We get a closed-loop system in its most abstract form, where the plant and controller state space models are shown. When we close the loop, you get a single system for the aircraft response. We will show how to derive this system later in this lesson. After some tuning, we test the tracking response with simultaneous airspeed and pitch angle commands. From the trim condition, we observe reasonable tracking. Note, the pitch angle on the bottom plot has a small bias error, which is expected since only proportional control is used. The airspeed tracking is asymptotic because there's an integral in the loop. Starting with the closed-loop aircraft model, we note that we desire an exponential altitude path, so we consider how to develop an altitude model. Note that h dot is Vt times sine of the flight path angle, gamma. But gamma is small, so it's approximately Vt times gamma. And note that gamma is total flight path angle. That is, the trimmed flight path angle plus the incremental change in the flight path as captured by the linear model. Thus, at the plant output, we explicitly note that incremental change to gamma and add trimmed gamma to produce total gamma. Then we can immediately determine h dot by multiplying by Vt. Integrating gives altitude. Thus, we have created the altitude dynamics, which is a new process at the output of the closed-loop aircraft. We can write the altitude dynamics as a state space model, where we create the output equation to produce altitude and altitude rate h dot. From the vantage of the flare path controller, the closed-loop dynamics of the aircraft and the altitude response are altogether the plant or the process to be controlled. To create a single system, we connect in series the closed-loop aircraft dynamics with the altitude model, where we've represented the altitude model in matrix form and now their connection in block matrix form, ultimately as a single matrix LTI system of equations. The system receives the command inputs Vt and theta through R, as well as the trimmed flight path angle input, gamma star, and its output Y contains altitude and altitude rate. We'll further refer to this as the plant, which we will control using the flare path controller. We now develop the flare path controller with the plant. The rate of descent is controlled through pitching the aircraft. At the pitch command input channel, we have the lead compensator and a proportional integral controller or coupler. The intent of the lead compensator was to allow for higher performance of the flare path controller, that is, to prevent the aircraft from touching down too soon. The controller operates on h-dot error. H-dot is a good choice for the track variable since rate of descent for safe landing is the primary concern, and the quantity could be measured with a radar altimeter. The plant model provides achieved rate of descent. It's fed back to a junction. We need h-dot command also at that junction. Recall the altitude rate equation. We multiply the fed back altitude by 1 over tau. This produces h-dot command, which we feed back in for our controller. This is the flare path controller without the lead compensator. To model it in state space, first define h-dot error. Integrate error to create a new variable ei h-dot, or the integral error of h-dot. Now, differentiate that variable. We get a state space equation where ei h-dot is the state. With this, we form the output model containing the integral and proportional components of the controller. Now, to connect with the plant output, we substitute h-dot command into our controller. We can now see the dynamic controller receives the plant feedback signals only. Achieved altitude, achieve altitude rate. Note that the plant receives the commanded airspeed. This is input to the airspeed controller in the plant, but we would like to make VT command part of the flare path controller as an input. So we simply add 0 times VT to the dynamic controller equations. Now, this has no effect at present, but it allows us the opportunity to create a new row in the output equation so that VT command can be passed through the dynamic controller into the plant. In matrix form, we simply have another LTI system with both feedback channels, Y, and the airspeed command input channel. We have the lead compensator. We connect that in series with the flare path controller, thus producing our full lead compensated flare path controller or flare path coupler. We finally have the plant and the controller. We are now ready to close the loop between these two systems. Let's derive the closed loop system in state space form. Start with the controller output equation R. The plant output Y goes into the controller equation. Make that substitution. Notice R appears both on the right and left-hand sides. Bring R to the left-hand side. Factor to obtain a matrix Z, and invert Z against the right-hand side. We now have an equation for R. Let's feed this into the plant. The plant, with the substitution of R, results in a right-hand side with XC, controller states, XP, plant states, and inputs gamma dot and v command. This is the closed loop plant equation. Now we derive the closed loop controller equation. We'll need the input y, which we note depends on r. We've determined r, and we substitute it into y so that we capture the effect of the controller on the plant output. We now substitute y into the controller equation, the xc equations. We expand, and this is the closed loop dynamic controller equation. Together, the closed loop plant and the closed loop controller have on the right-hand side states of xc and xp and inputs of v command and gamma star. The output to the closed loop controller is y, and it's these equations that constitute our full closed loop system. They can be written in block matrix form. And simply in matrix form, we'll denote them with the subscript CL for closed loop. We have our final result, the closed loop flare path control system. It receives airspeed command input, VT, trimmed flight path angle, and it produces the achieved altitude and altitude rate. It is represented as an LTI model, and once integrated, any state of the closed loop system can be inspected from the solution of the state equations XCL. To summarize, the closed loop system contains the aircraft airspeed control, the pitch control, multiple lead compensators, control actuation system models, altitude and rigid body dynamics, and of course, the flare path controller. We will simulate this control system as if we are transitioning from the glide slope at 40 feet of altitude. The trim state is -3 degrees flight path angle, holding 250 feet per second airspeed constant. The angle of attack is near zero, so that the aircraft then is pitched down 3 degrees initially. This condition requires 29% throttle and about 15 degrees of elevator, trailing edge up. This is the linearized system about this trim condition. The eigenvalues show the short period and the phugoid modes, complex pairs. The short period has significant damping, 0.55, with a natural frequency of 1.06 radians per second, or 0.17 hertz. The phugoid's stable, surprisingly damped, but characteristically slow, with a time to halve of 40 seconds, much slower than the short period time to halve of 1.19 seconds. We'll need to set up the geometry of our flare path. We define the rate of descent time constant with range from the transmitter to touchdown, R2, trimmed airspeed, and number of time constants to touchdown, N. With tau determined, we have the altitude rate command equation. We set the initial altitude at 40 feet. So our overall control objective is to hold airspeed and follow the commanded rate of descent. After some tuning, we arrive at reasonable tracking performance. The top chart shows airspeed tracking. The bottom chart shows altitude rate, or H dot tracking. Note the small excursion in airspeed as the aircraft attempts to follow the commanded altitude rate. This excursion is less than 1% of the trimmed airspeed, and it ultimately recovers. To learn more about airspeed tuning, check out section 1.6.3. The altitude rate shows an underdamped response, but ultimately tracks well. Integral control plays a key role in achieving this response. Integrating the commanded altitude rate and comparing to the achieved altitude shows reasonable tracking. The rate of descent is effectively reduced according to the exponential command. Inspecting states of the full simulation, we observe a throttle and engine response well within limits, although the aircraft does have to increase throttle to land. The pitch angle tracks the command, but there's a 1-degree bias error. Adding integral control to the pitch angle control loop could help eliminate this error. The angle of attack is aligned with the aircraft fuselage out the nose as it lands. Pitch rates are small and do show some fluctuation prior to converging to zero. The oscillation in the pitch rate loop is not directly due to the pitch control system. As our previous plot showed, excellent pitch command tracking. Instead, this oscillation is an outcome of tuning the flare path coupler. The elevator adjusts according to the commanded pitch angle from the flare path coupler and is well within its limits. The integral error of h dot, altitude rate, it grows initially, then levels off, indicating that additional error is not being added to the integral. That is, tracking is achieved, and this is consistent with our altitude rate plot shown earlier. Animating these results, we hardly notice the oscillation. We observe a smooth and controlled landing with the reduced rate of descent for safe touchdown achieved. Access this lesson and more at learngnc.com, and a sincere thank you to my Patreon subscribers who gain access to all the codes in this analysis, lesson previews, in-depth video discussions, and code tutorials. You make this content possible. Thank you again.